In today's session, we'll be discussing the previous year questions from the aerodynamics portions of the 2015, right? So this is the marks distribution. So we have around 5 1-mark questions and then 5 2-mark questions. So totally around 15 marks from the aerodynamics concepts, which is quite substantial. So let's get started. For a constant free stream velocity and density, a change in lift for a large aspect ratio straight wing with thin cambered airfoil section at small angle of attack leads to, what they're saying is you have a wing with very large aspect ratio. Uh, Imagine it's almost like an airfoil kind of a flow physics, because your aspect ratio is so large that your 3D effects can be neglected, right? And the free stream velocity v infinity and rho infinity are basically constant. And what they're telling us that there's a change in lift for this particular wing, and it is happening at a small angle of attack. So it's at very small angles of attacks, not very small, extremely small, but some small angle of attack. There's a change in lift that is happening. So lift basically became from L to L plus delta, right? So we can imagine that if velocity and density are remaining the same, what probably is changing the lift is nothing but your change in angle of attack. So let's say your alpha became alpha plus delta alpha, because there is nothing else, right? Because anyway, the 3D effects are neglected, so it could not be that which is creating a small change in the lift. So ultimately, it should be the alpha, the angle of attack, that is creating this change in lift. So what they're asking is that what it leads to. So it leads to a shift in the aerodynamic center and no shift in the center of pressure, a shift of the center of pressure and no shift of the aerodynamic center, a shift of both aerodynamics and center of pressure, and no shift in either of them. They're asking what is actually changing here, whether my aerodynamic center is changing or what exactly is happening here. So we know that here, the change in lift has happened because of change in angle of attack. And we know that aerodynamic center does not change with angle of attack. But we know that the center of pressure, its location can change with angle of attack, because center of pressure is nothing but the location where your resultant of all your forces act. So if your lift is changing, so what can easily happen is that your location where your resultant of these forces are acting, uh, resultant of both lift and drag, can definitely change, because you have a change in the force, so correspondingly there should be a change in the location where your net moment goes to 0. Um, uh, so the right option here is option B, that there can be shift in the center of pressure and no shift in the aerodynamic center. All right. Any questions? The primary purpose of a trailing edge flap is avoid flow separation, increase CL max, reduce wave drag, reduce induced drag. So we know that the trailing edge flap, cannot really, delay any flow separation or reduce induced drag or reduce wave drag, because that's not the point of a trailing edge flap, right? So the main purpose of it's basically increasing the CL max. So one of the few sessions back as well, we had discussed how does the flap work. So the flap will basically shift your CL versus alpha curve. So let's say something like this. So actually, your value of your CL max is actually increased now with the deflection of a flap. About stall angle of attack, so there can be some changes in stall angle of attack, but that primarily happens with the use of slats, not trailing edge flaps. Trailing edge flap might, more or less retain the same stall angle, but create for the same stall angle, create an increase in the CL max. Right. Mhm. So the right option here is option B. Consider a monoplane wing and a biplane wing with identical airfoil sections, wingspans, and incidence angles in ideal conditions in a wind tunnel. As compared to monoplane, the biplane experiences. So monoplane, biplane are nothing but, um, you know, you have the if it's a one wing configuration, it's a monoplane, and biplane basically have two wings stacked one above the other. And they're saying that they have identical airfoil section, wingspans, and incidence angles in identical conditions in the tunnel. So everything is identical for these two guys. So as compared to monoplane, the biplane would experience higher lift and higher drag, higher lift and lower drag, lower lift and lower drag. So basically, they are asking us to compare the lift and drag for these two configurations. So usually, what happens is that a biplane, because of there are two things which contribute to a higher lift in a biplane. So there can be the biplane again, has um, two airfoil sections, two wing sections that will contribute to additional lift. And at the same time, as you can see, some of the induced drag effects, from let's say from the bottom wing, from the top wing will be inhibited by the bottom wing, and from the whatever the induced drag effects from the bottom wing will be inhibited by the top wing. So hence the effect of the 3D effects are quite lesser in a biplane kind of configuration. So you'll have higher lift, and this will also a higher drag one if there is, because you have now two lifting surfaces, so there can be skin friction corresponding to these two surfaces. And plus, at the same time, you have other sorts of drag like the interference drag when you add in more components to your system. So hence, you will have higher lift and higher drag in case of a biplane kind of configuration. Right? Questions here? Consider a wing of elliptical platform with aspect ratio infinity. Its lift curve slope dCl by d alpha is. So they're asking you have a wing which is elliptical in shape and its aspect ratio is infinite. So they're asking you what is the dCl by d alpha for this entire wing configuration. Uh, so we know that the lift curve slope of a wing is related to the lift curve slope of an airfoil as A naught by 1 plus A naught divided by pi AR in for an elliptical um, planform scenario, right? And if my AR is infinite, so this term basically goes to zero. My A equals A naught. So my lift curve slope of my airfoil and the same as the lift curve slope of my wing. So you can, for this question, they want some numerical value, so you can assume A naught to be around 2 pi from thin airfoil theory. So that would be around 2 into 3.14. So that will be around 6.28. Yeah, questions? Let's move ahead. The Reynolds number Re is defined as UL by VL by nu, where L is the length scale of the flow, U infinity is the reference velocity, V is the coefficient of kinematic viscosity. In the laminar boundary layer approximation, comparison of the dimension of the convection term and the viscous terms leads to the following relationship between boundary layer thickness and Re. Um, so they're asking you what is the relationship between boundary layer thickness and your Reynolds number. And we know that from Bloch's solution that your delta is related to your Reynolds number as some constant divided by delta by x is nothing but some constant divided by root of Rex. Uh, so in this case, um, the right option is nothing but, so your delta is directly proportional to 1 by root of the Reynolds number. So option B is the right. All right. Now let's look at this. For a thin flat plate at 2 degrees angle of attack, the pitching moment coefficient about the trailing edge is. They're asking you for a thin flat plate at 2 degrees angle of attack, what is the, let's say you have a flat plate like this. Just read for that. So you have a flat plate like this, and it's at an angle of attack of 2 degrees. Now for this, what is the pitching moment coefficient about the trailing edge? If this is the trailing edge, and what is the pitching moment coefficient? So we can use the concept from thin airfoil theory, because essentially the thin airfoil theory would basically take a thin symmetric airfoil and then assume it as a vortex distribution over its chord line, which is nothing but like a kind of a flat plate, right? Uh, so we can consider the case of we can draw the equivalent of a thin flat plate to a thin symmetric airfoil. If you have a thin symmetric airfoil, it's pretty much similar to that of a flat plate. All right. So for a thin symmetric airfoil, we know that the um, a pitching moment coefficient at the leading edge is nothing but minus CL by 4, which we have already learned and derived from a thin airfoil theory. So the moment coefficient at the leading edge is nothing but minus CL by 4. So moment at the, and then you also have the lift acting over here. So moment at the trailing edge is nothing but moment at the leading edge plus lift into your chord length. So from leading edge to trailing edge, the distance is chord length, right? C, let's say, or whatever is the length of the flat plate. Okay. If I convert them to moment coefficient, so this is Cm at the trailing edge equals Cm at the leading edge plus CL for that matter. So coefficient of moment at the leading edge is minus CL by 4 and plus CL. So this will be nothing but 3CL by 4. And this and you have a thin flat plate at 2 degrees. So CL can be evaluated as 2 pi alpha. And alpha here is 2 degrees, so converting it to radians. So 2 pi into 2 into pi by 180. Right. So your coefficient of moment at the trailing edge is nothing but 3 by 4 into 2 pi into 2 into pi by 180. and this would turn out to be a value of around 0.164. On this. Go ahead. The velocity profile for an incompressible lamina bond layer or a flat plate developing under constant pressure is given by u by u infinity equals 3y by 2 delta minus half y by delta whole cube. Free stream velocity is 10 meters per second and dynamic viscosity is 1.8 10 power minus 5. At a streamwise station, the bond layer thickness is 5 mm, the wall shear stresses. So basically, they're telling you, there's a flat plate, there's a boundary layer developing over the flat plate, and let's say at any given location where boundary layer is delta, the profile of the velocity varies by the equation. I've told you what is u infinity and what is mu. Now they're telling there's a streamwise location where the boundary layer thickness is 5 mm. So somewhere from the leading edge, let's say at some x meters from the leading edge, there's a location where delta is 5 mm. They're asking us to find out what is the wall shear stress. So wall shear stress is related to velocity as mu into dou u by dou y according to Newton's law of viscosity for a Newtonian fluid. Right. So let's evaluate this. So this is mu into dou u by dou y. So if I differentiate this, this will be nothing but a by 2 delta minus half into y cube. I'm sorry, y square by 3 y square by delta cube. Right. And you want wall shear stress. So this needs to be evaluated at y equals 0. Okay. You want to evaluate the stress exactly at the location of wall. So when I substitute y equals 0, this goes to 0, and this will become mu into 3 by 2 delta. And you have your sorry, this into u infinity. So there's a u infinity to be multiplied over here. So this into u infinity. If I substitute the values, so we have 1.8 into 10 power minus 5 into 3 into 10 divided by 2 into 5 mm, converting it to meters, 5 into 10 power minus 3. You'll find that the wall shear stress takes a value of around 54 into 10 power minus 3 pascals. So that is basically the value of the wall shear stress in this scenario. Right. Next question. The pitot tube of an aircraft registers a pressure P naught, which is equal to 54,000 P1. The static pressure density and specific ratio heats of free stream are P infinity 45,565 and rho infinity and gamma equals 1.4 respectively. They're asking you the indicated speed. All right. So typically when we were finding the indicated airspeed, what we would do is you would basically use Bernoulli's equation, and then for a pitot-static tube, and you calculate it as P naught minus P infinity divided by rho infinity. But this is only true for an incompressible kind of a scenario. So for a compressible scenario, because we still don't know what is the Mach number of this situation of this scenario, if it is greater than 0.3, then probably we'll have to use our Bernoulli's equation will probably give you errors in the calculation. So let's use the gas dynamics relation between P naught and P to evaluate the Mach number. So P naught by P equals 1 plus gamma minus 1 by 2 into m square whole power gamma by gamma minus 1. Okay. So P naught is 54,051. 51 divided by 45565, and I need to raise it to gamma minus 1 by gamma, which is gamma is 1.4, so this would be 0.4 by 1.4, and that is equal to 1 plus gamma minus 1 by 2 is nothing but gamma 1.4 minus 1 by 2, which is 0.2 into m square. If you were to do this calculation, your m will turn out to be a value of 0.5, which is greater than 0.3. So it's a compressible scenario. It's a compressible kind of a scenario. So if you were to use this to find the velocity, it would give you errors. All right. So then, now since we have the Mach number, you can actually find the velocity from the Mach number. So Mach number is nothing but velocity by root of gamma RT. Right. So you have Mach number as 0.5, your velocity is something to be found out, and your gamma is 1.4, R is 287, times your temperature that you need to figure out. So temperature you can evaluate from ideal gas equation. So P infinity equals rho infinity R into T infinity, right? So they've given you what is P infinity, which is measured from the static probe. Rho infinity they have given, R is also known, R is a constant, so only T infinity is left out. This would be V divided by square root of 1.4 into 287 here, and T is nothing but your P infinity, which is around a value given in the question as 455 6 45565. Your R is 287, and your rho is given as 0.6417. 0.6417. All right. So essentially, your velocity turns out to be 157 meters per second, right? Which is nothing but your indicator speed, right? So option A is the right answer over here. Now, if you were to do it by the Bernoulli's equation, what would happen is that you will get answer B, and which is wrong, and hence you would be, though it's not that off by a very large value, but then it would still be the wrong answer. Right, so always check for compressibility. Now let's go to this problem. Consider a NACA 0012 airfoil of chord C in a free stream with velocity V infinity. So this thing, you have a NACA airfoil with whose chord length value is C, and so let's say this is it's a symmetric airfoil, and it's in a the free stream velocity is V infinity, and the chord length is C, right? and the angle of attack is alpha. The average time of flight for a particle to move from the leading edge to the trailing edge on the suction and the pressure sides are T1 and T2, respectively. So suction side is the top portion, and the pressure side is the bottom portion. And the average time of flight, basically, so particle wants to move from the front to the back. T1 and T2 are the average time that it takes, one on the top side, another on the bottom side. And according to thin airfoil theory, the velocity perturbation of the free stream on the suction side and the pressure side, where theta corresponds to the chordwise position. So what they're telling us is that if I take any location on my top surface, my velocity, so they're saying these are the velocity perturbations of the free stream. So which means that at any given location on the top, my velocity top, V top, let me just write it as V top, equals V infinity plus V infinity into 1 plus cos theta into alpha by sine theta, right? And velocity at the bottom at any given location, velocity bottom is nothing but they've given the velocity perturbation in the section in the pressure side or the bottom side as minus V infinity 1 plus cos theta into alpha by sine theta. So this is V infinity minus V infinity into 1 plus cos theta into alpha by sine theta. So this is basically the scenario. Now they're asking you what is the difference between T2 minus T1. So we know that the velocity is slower on the bottom side. It will take more time for the particles to reach the top from the front to the back. So so T2 will be larger than T1, and what is that particular value? All right. So let's just try and figure it out. So we know that T2 and T1 are nothing but the average time of flight. That is, so T, that is the time taken, is the average time, which is nothing but your average, basically your distance that it covers in along, so from front to back, it covers a distance of c divided by the average velocity that it takes. So your time taken, T average, is nothing but the distance that it covers divided by basically the average velocity, right? So it's covering a distance along so much along the x-axis, and the average velocity is v average, right? So now if you take the t1, that is the velocity time taken for the particles on the top surface. So this is nothing but c divided by the average velocity on the top, the average top, and T2 is nothing but the c divided by the v average on the bottom, right? Then now we need to calculate what is this average velocity at the top and bottom. So v average top will be nothing but, we know what is the velocity at every single location, right? We know what is the velocity at every single location, which is nothing but v infinity plus v infinity into 1 plus cos theta into alpha divided by sine theta, right? This is what we know as the average velocity. And this, if I were to integrate with respect to x, because my, the coordinate system is x, not dx, x, And then if I divide it by the entire length scale in the x direction, that is integral of dx, that basically gives me my average velocity. So I'm averaging it along the along every location, and then dividing it by the total length scale in that in that particular direction. All right. So this is how you would calculate the average velocity in the top. And similarly, average velocity in the bottom will be nothing but v infinity minus these terms. All right. Now let's try and evaluate this integral. So you have so your x is nothing but c by 2 into 1 minus cos theta. So here we have integral in terms of x, but my terms are in terms of sine theta and cos theta. So let's and this integral would be from x equals 0 till x equals chord. So this will be from 0 to c, 0 to c. All right. And we can straight away see that integral of dx from 0 to c is nothing but the chord length itself, right? Because it's just x is just the axis. So if I integrate dx along this entire length from 0 to c, it will be just the chord length itself. So let's focus more on the numerator. All right. So we average the top is nothing but integral 0 to c v infinity plus v infinity into 1 plus sine theta sorry 1 plus cos theta divided by sine theta into alpha whole thing into dx and divided by c, because integral dx 0 to c is nothing but c. Now they've given you x equals c by 2 into 1 minus cos theta, right? So if I find dx, it would be nothing but dx equals c by 2 into sine theta into d theta. D theta. And my limits, if my x is 0, if I substitute x as 0, I'll find my theta to be 0. All right. And if I substitute x as c, you can substitute the limits and write out. It's very trivial. So if I substitute it as c, then my theta will turn out to be around pi. Right. So now the limits of the integration would change from 0 to pi. So average velocity at the top now is given by integral 0 to pi, and then there is a c in the denominator, so I'm going to write it as 1 by c. To I can take v infinity outside both these terms, right? So let me take the v infinity. V infinity is not dependent upon any of those x locations. You'll have 1 plus cos theta by sine theta into alpha, and the whole thing into dx now became c by 2 sine theta d theta, c by 2 sine theta d theta, right? So now I can take this c outside the integral, 2 outside the integral, and then this c and this c would cancel out. So you'll have v infinity by 2, and then integral 0 to pi. So multiply sine theta inside, so this will become sine theta plus sine theta, and this sine theta would cancel out, and you'll have alpha plus cos theta into alpha into d theta. All right. So now let's do the integration. So this would basically become v infinity by 2 sine theta. Integral of it will be nothing but minus cos theta applying the limits 0 to pi. Integral of alpha will be nothing but alpha into theta, 0 to pi, right? And this would be alpha into sine theta to pi. So now let's evaluate, one by one. So your cos of pi is -1, and minus of cos of 0, that will be 1, and there's a negative sign altogether. So this will be nothing but +2. And this will be alpha theta. So this will be, alpha into pi minus alpha into 0. So that will be pi alpha, right? And here sine theta you have. So sine theta is 0, both at pi and 0. So this term will basically go to 0. So finally, your average velocity on the top will turn out to be the average top will be nothing but v infinity by 2 into 2 plus pi alpha, right? And similarly, your t at the top, which is nothing but t1, is going to be c divided by velocity average at the top, which is nothing but 2c divided by p infinity into 2 plus pi alpha. Right. And now if you were to find out what is the average velocity at the bottom, v bottom, again we have to perform this integral. Bottom is nothing but integral 0 to c. Velocity at the bottom is v infinity minus v infinity into 1 plus cos theta into alpha by sine theta into dx divided by integral 0 to c into dx, right? You do this integration just similar to what we did before, and finally you'll find that the average velocity would look something like this at the bottom, v infinity. So since we don't have a lot of time in the session, so I'm just going to give the answer. It's very straightforward. You guys can try it out. So it'll be v infinity by 2 into 2 minus pi alpha. All right. So this is the average velocity at the bottom. So hence T2 would be nothing but C divided by the average bottom, and that would be nothing but 2C by V infinity into 2 minus pi alpha. So now you need to go and figure out what is T2 minus T1. T2 minus T1 will be nothing but 2C by V infinity into 2 minus pi alpha minus 2C by V infinity into 2 plus pi alpha. If I take 2C by V infinity common, this would be around 2 plus pi alpha minus 2 plus pi alpha divided by 2 minus pi alpha into 2 plus pi alpha, that is 4 minus pi square alpha square. So this would be nothing but 2 cancels. You have 2 pi alpha, and so that becomes 4 pi alpha c divided by v infinity into 4 minus pi square alpha square. Nothing but t2 minus t1. The right option here is option C. Right? Any questions here? Let's look at the next problem. Consider a 2D blunt body in compressible fluid stream. The flow is rotational and can be modeled as a linear combination of uniform flow and a line source. So basically a Rankine half body. Let S be the distance of the line source from the front stagnation point. So from the line source to the front stagnation point, S is the distance. Let D be the upstream distance from the stagnation point to a streamwise location where oncoming stream reaches 90% of this undisturbed value. So from this stagnation point, if you go a distance D, you'll reach a point P. So velocity at point P, what they're saying is that, it's 90% of your free stream value. All right. So what they're asking us to find is what is D by S. All right. Now we know that for a Rankine half body from our incompressible, calculations, the potential flow theory, my VR is given as V infinity cos theta as gamma by 2 kappa by 2 pi r, and my V theta is nothing but minus V infinity sine theta. Right. So this point is basically, at a distance s from the front stagnation. So this point is basically from the line source to the front stagnation point s. So s we already know in any standard textbooks. If you calculate the distance of the stagnation point from the line source, it is nothing but kappa by 2 pi v infinity, which is already, you can find the reference to it in any of your standard textbooks. That so line source is the location of the line source is basically taken as the origin for this kind of flow field, and from the origin it is at a distance of kappa by 2 pi v infinity in theta equals to pi direction. So this is basically theta equals pi direction. All right. Now in the same pi direction, if I go to point P, we have to figure out what are the velocities. So when theta equal to pi, my v theta is 0. All right. My v theta is 0 at point P. Right. Now I need to figure out what is VR at point P. So if I substitute theta equals pi over here, so this basically gives me minus v infinity. And I have gamma kappa by 2 pi r. So r is nothing but distance from the origin to point P. So distance from the origin to point P is nothing but d plus s. This is by 2 pi to d plus s. All right. This is my VR at that location. And they have already also told you that my free stream velocity, this is the free stream velocity at point P is nothing but 0.9 times v infinity. And you can see the positive direction of your VR is radially outwards, but velocity at this point is, point P is radially inwards. So basically it is in the negative direction of the convention. So VR at point P, velocity at point P, that is nothing but the radial velocity at point P is nothing but negative of 0.9 times v infinity, because by convention radially outwards is positive, but here, as you can see, it's the 90% of the undisturbed velocity. So 90% the free stream is in the opposite direction to that of the radial direction, right? So It's minus 0.9 V infinity. Now, if I substitute what is what is VR at that location, it is minus V infinity by kappa by 2 pi into d plus s, and that is equals to 0.9 V infinity. And if you go to rearrange and find out what is d plus s, it will turn out to be a value 10 kappa by 2 pi V infinity, right? And s is already known to us. S is nothing but kappa by 2 pi V infinity. Kappa by 2 pi V infinity. Here d in this case would be nothing but, if I just take this to the other side, this will be 9 kappa by 2 pi V infinity. And so in our case, so d by s would be nothing but the ratio of this kappa 9 kappa by 2 pi V infinity divided by kappa by 2 pi V infinity. Okay. So kappa cancel, 2 pi infinity cancel, so your d by s will turn out to the value of 9. The right option here is d by s is 9. Right? Questions here? Negative infinity, because your VR, so in the circular coordinates or the polar coordinates, any radial velocity VR is taken positive radially outwards, right? But at location P, though along your x, y coordinates, this is in the positive direction because the velocity here is in this way. But according to your radial coordinates, this is coming in radially inwards. So it must be negative, right? If it was in xy coordinates, it would be positive. But since it is these radial and theta polar coordinates, that's why we take it as negative. So yeah, that's all for the session. Thank you guys. So if the stall angle of attack increases or decreases, it's function of slat. Yeah, it's function of slat. Any other questions? Okay. All right then. Yeah. Thank you. I'll see you all in the next session.